Okay, so hi everyone. So as I don't have to tell this audience, we all know that brain disorders are a leading cause of disability, but unfortunately, our current treatments fail tens of millions of patients. Let's think about major depression, for example. So the question becomes, what do we do for these people? Now, based on the understanding that these disorders are actually signs of abnormal activity across the brain, one way to think about this that we're doing in my lab is to try to directly decode and regulate these abnormal activity patterns towards potentially transformative therapies. Now, these are the activity patterns that we can record intracranially from the human brain, and I think the animation is not working. But anyways, you can see that these are complex spatiotemporal patterns which are very noisy. So what we envision is, let's see. Okay. All right, so what you can envision in your brain is that we build a system that models these activity patterns, decodes from them an underlying state of the brain, let's say mood in depression, and then uses that as feedback to adjust the therapy parameters, let's say DBS amplitude and frequency, in order to take the brain to a target healthy state. Now, this is an example of a closed-loop system, but it doesn't exist for the brain, and actually it's very difficult to build it. So what we've been doing in my lab is to address several challenges towards realizing these systems. The first challenge, of course, is to build a decoder. Now, back in 2018, we actually developed, okay. I don't know. So we developed dynamical system modeling approaches that could decode mood from human intracranial brain activity as related to depression and anxiety. And this was very exciting, of course. But in order to make these translate, we have to significantly improve accuracy and robustness. And a major barrier to that is that we have limited data per individual. So how can we overcome this barrier? And what we're doing now is to tap into the power of AI by developing brain foundation model that can actually aggregate data across many individuals to pre-train the foundation model, agnostic to any behavioral labels, such that then you can use in a new subjects their limited data sets for just fine-tuning and have these models generalized both across subjects and across tasks. But if you think about intracranial recording, one major challenge to doing this is that these electrodes are very sparse and heterogeneous from subject to subject, and they also have very complex spatiotemporal relationships. So how do we address this? Actually, if you think about it, current neurofoundation models do not impose any kind of spatial encoding. They either ignore space or they do it at the level of single channel. So in new work that I'm showing actually for the first time here, what we did was to introduce a new method called Barista that can incorporate flexibility in spatial encoding and pick the right spatial encoding for neurofoundation modeling of IEG activity. Whether the spatial encoding, for example, is at the level of individual channels, at the level of brain regions or atlas parcels, or even at the level of brain lobes. And the way we do this is through the process of tokenization. So what we do is we take neural activity and then we encode during tokenization both temporal patterns as well as a spatial designation to turn the activity into latent tokens that are input into the transformer that is then trained self-supervised. Now, doing this, then we can train also downstream decoders for various behaviors. Now, as a first proof of concept, we used a benchmark data set called Brain Tree Bank, where subjects are watching movies, and our goal was to decode auditory and visual features from neural activity. For example, whether there was speech or no speech during a given neural segment. And what we found that indeed pre-training across many subjects significantly improves performance. But more interesting than that, by encoding spatial information at scales larger than individual channel, Barista can actually outperform state-of-the-art IEG neurofoundation models given that spatial encoding. These results extended to different downstream tasks. They also extended to left-out subjects and scaled with more and more pre-training data. So we're very excited. This is just the first step for us, and we're very excited to take this approach into different domains of neuroscience and neurotechnology to start to address this first challenge. But even if we do that, unfortunately, that's not enough, because if you even perfectly decode a brain state, you still don't know how to stimulate the brain in order to regulate or change it. So the next challenge we're working on is to build input-output models that describe the effect of stimulation and inputs on brain activity. And we've done this through linear dynamical system modeling. And the reason we kept our original models linear is because they're amenable to building real-time closed-loop systems. But of course, there's no linearity in the brain. So the step we're currently taking is to develop AI architectures that both capture nonlinearity, yet at the same time can enable real-time inference and decoding. Finally, a main challenge we're working on is that these activity patterns that we record from the brain do not just relate to the behavior that we're interested in decoding. So let's say right now you're trying to decode my mood, I'm also moving my arm, I'm talking to you, maybe I'm hungry. So what we're doing is develop approaches that then disentangle those brain patterns that are related to the specific behavior of interest. We're incorporating the effect of input within these models, and we recently developed an AI model for neural behavioral data, can do this disentanglement and capture nonlinearity. And we're making all of these technologies multimodal, whether you're thinking about electrophysiological recordings, neuroimaging, magnetic, acoustic, optical, whether you're thinking about variables and physiology, we're fusing information to get the best readout. We're also doing different modalities, of course, writing, magnetic, acoustic, and optical. And because these are multimodal, we're hoping that these systems and algorithms can easily extend to a variety of devices that are being developed today by a lot of beautiful startup companies, as well as a lot of brain disorders, from mood to chronic pain to obsessive compulsive and movement disorders. So basically, our final vision is to have this generalizable AI-based system that both extracts these behavioral and mental states from the human brain and regulates those states. So thank you very much.
Thank you, very interesting. I was wondering what kind of self-supervised tasks you used for that foundational model, and how did performance scale on those metrics, not on the downstream tasks, but just on the self-supervised.
The specific task we used here was actually latent token reconstruction, so JEPA style type latent reconstruction that we had. I don't know what you mean by exactly how scales on this, because depending on what kind of pre-training you use, you have different measures that you're optimizing, so it's hard to compare actually with other ones. The only kind of ground truth we have is either neural reconstruction or behavioral reconstruction, and we had both of those tasks, and in both cases, it was outperforming the state of the art. Yes?
How many participants do you have? And you talk about generalization. How does generalization scale as a function of the number of participants?
So that's a great question. So this was a benchmark data set that has about 12 participants and about 2-3 hours per participant. And as you see, we saw scaling versus the amount of training data, but it was kind of saturating already. I want to emphasize this is decoding like visual auditory features. So these are simple tasks. I anticipate as we have more and more data and as we have more and more tasks, we would actually see more and more benefit from that.
No question?
If you had $5 million to create a data set that would accelerate all of this? Like, what would that look like, and how would you optimize it?
It depends on what you want to do with it,
What
right?
do you want to do? What do you think is the coolest thing?
Well, I have my own dreams.
Go for it.
But I mean, it depends on the task. For example, if you're interested in a foundation model largely in the sensory motor system, the tasks you would design are more naturalistic movements that take natural stimuli and generate movement. If you think about something like cognitive states, then you want to design tasks that can basically invoke complex cognitive processes such that you have measurements of that. And if you want to build a foundation model for all of that, you want to have a data set during essentially naturalistic day-to-day life. So $5 million is not going to cut it, of course, for that. But we can start somewhere. Thank you.